Okay, good morning, everyone. We were discussing uncertainty in component values, and there are some systematic uncertainties that result because of process and temperature. We looked at that. We consider them for now to be common across the chip. Now, there will also be uncertainties because of the way you physically lay out the components. We saw how to avoid those things. Essentially, you should try to make identical elements as much as possible in identical environments. That's when you will have characteristics that are closely matched. Now, even after doing all of that, it turns out there will be random variations. This is similar to coin tossing and throwing dice and so on, right? So you can't predict exactly what comes out. So that's why even if you make nominally identical rectangles for resistors, you make large number of them, their distribution will show some spread. Okay. And if that is the case, there are every circuit will be affected by it, and you have to be able to calculate what effect it has. So, for instance, if we have an amplifier like this, the gain magnitude is R2 by R1, and if R2 is nominally R2 0 plus it has an error delta R2, R1 is nominally R1 0 and has an error delta R1, we saw that this will really be R2 0 by R1 0, 1 plus delta R2 by R2 minus delta R1 by R1. Okay. And this is really the nominal gain A naught times 1 plus delta A by A naught. Okay. So you can clearly see that the nominal gain is that one. Okay. And the delta A by A naught is related to that. Okay. This is a simple circuit, and then in this case, the relative error in the gain delta A by A naught is related to the relative error in the resistors. In fact, in a large number of cases, we'll see that for most of the cases, we'll see that it's the relative error that is described. Okay. Now, this being a statistical quantity, you are not looking at delta A for every amplifier, but you just want to know if you make, let's say, 1,000 amplifiers, what will be the distribution of the gains. Okay. So that also will be Gaussian distributed. So if you plot versus A, the distribution will be centered around A naught and it will have some variance. Okay. So now what will be the variance of delta A by A naught? What is it going to be? Variances? So we assume, and this is true, that for physically different components, the errors will be uncorrelated. Okay. So in that case, this delta R2, basically delta A by A naught is delta R2 by R2 minus delta R1 by R1. Okay. If the errors are uncorrelated, their variances add up, right? Okay. So in this particular case, the variance of gain error, relative gain error, is the sum of variances of relative resistor errors. There are two resistors here. Okay. Now, what is the variance of the resistor error? That is something that, of course, it depends on the process, but you also have to know what is under your control, right? So the question is, how does, let's say, the resistor relative error depend on the parameters a designer can control, and what can a designer control in a resistor? W and L. Okay, so that's what we have to find out. So let's do this exercise. So let's say we have a resistor R that is nominally R naught and has some error delta R. Okay, and then there is some variance. I'll just call it sigma R square. This is by definition the variance of the relative error. Okay, I will illustrate this with a specific example and then generalize. You will see that it's reasonable. So now what I'll do is I'll connect 4 units of these together. Nominally they're all the same. Okay, I do this. And R1, R2, R3, R4 are just 4 copies of the same resistor. What is the nominal value of this? R0. It's just 2 resistors in series, 2 of those in parallel. So this is R0. Okay. Plus it will also have some error, delta R prime. Okay. So now the question is, what is sigma R prime square? That is variance of delta R prime by R0. What will it be? What do you think it will be? Please calculate it. I think you know enough basic probability to do this. And of course, you have to assume, it is reasonable to assume that delta R prime or delta R's for each resistor is much less than R0. Okay. All the 4 will be uncorrelated. Okay. They are basically avoid approaching the line. We have four resistors, not connected. So this sigma r square is variance delta r by r. Sigma r prime is relative error. Hope you okay. Forget the basic. Just get a what is the so just get an expression as plus r naught times 1 plus. Okay. The error is different. Okay. There are unrelated. So you get an expression of the forms r naught times 1 plus something. Okay. That something we can use. And both are the same. 1 by 4? Yeah. Okay, the first thing is you need to develop stamina for this minimum calculation at least. What is the resistance of this combination? It is 2R naught plus delta R3 plus delta R4, and the other one is 2R0, sorry, delta R1 plus R3, right? Delta R1 plus delta R3, this is delta R2 plus delta R4. Okay. So now what do we have? The parallel combination of the resistors. So the conductances will add up. So by the way, each one can be written as 2R0, 1 plus delta R1 plus delta R3 by 2R0, and the other one is 2R0, 1 plus delta R2 plus delta R4 by 2R0. Okay. And what I said is this part here is much smaller than 1. Okay. So what is the conductance of that? What is the conductance of the first one? It's 1 by 2R0 times the reciprocal of that, which is 1 minus delta R1 plus delta R3 by 2R0. And the other conductance is 1 by 2R0, 1 minus delta R2 plus delta R4 by 2R0. Okay. So now the total conductance is so 1 by R0 times 4. Yeah, is this correct? Okay. So what is the resistance? It's the reciprocal of this, which is there something wrong here? Okay. So the nominal value is R0. Okay. And each of these, the variance is sigma R square, right? So what is the variance of this quantity? Again, each resistor is uncorrelated from the other. The error in each resistor is uncorrelated from error in other resistors. So the variances add up. So you have 4 times sigma R square divided by 16. Okay. So sigma R prime square is 4 times sigma R square divided by 16, which is sigma R square by 4. I did it for this particular combination. Okay. So if you combine multiple resistors, the relative error reduces. Okay. Now, what I started off was by asking like what can the designer do to improve the reduce the resistor error. Okay. So how is it related to this calculation? So basically, if you look at this, let's say my resistor was this rectangle. Okay, originally. Here I did a specific calculation and then telling you the general rule. So this you can think of as having four rectangles, right? So if this had W and L, this has 2W and 2L. Okay. So basically it has 4 times the area. Now what happens is the errors in each, let's say it is the number of dopants. There will be something here, some random stuff there and something else there, something there and something there. They all get averaged out when you combine them. Okay. So that's why the relative error becomes smaller. So from this, I'll just tell you the general rule. So if you make the components physically larger, they will become more precise because these random errors will tend to get averaged out. Okay. So This is true for every component, but for resistors, basically it is given as something, the variance will be inversely proportional to the area. Okay. And first of all, I think you understand this. If you have uncorrelated errors from different parts, if you combine many, you can reduce the variance. Okay. And I just took the example where by combining 4 resistors, you have nominally the same resistance value, but a smaller relative error. Okay. But in general, the resistor error variance is inversely proportional to the area. And this constant of proportionality is AR square, or sigma R is AR by square root WL. Anyway, let me emphasize that this sigma R or sigma R square, this is related to the relative error, not the absolute error delta R. Okay. So, right. Now, this AR typically is specified in some percent times micron, basically the type of units that we prefer to use. Okay. So, this means that if AR is given as 1% micron, and if you have a resistor whose width is 1 micron and length is, let's say, 25 microns, whatever the value is, its relative error will have a standard deviation of how much? Huh? How much is the standard deviation of relative error for this resistor, which is 25 microns long, 1 micron wide? 0.2%. Okay. And from this, you can calculate what does, I mean, having a Gaussian distribution of some sigma mean? What can you say really? You must have heard of terms like 3 sigma, 6 sigma, etc. Right? What is 3 sigma? So 99.9% of the population will lie within that. So it means that if you make, let's say, 10,000 resistors of this size and then measure them, and basically 9990 of them will have values within in that range. Okay, 0.2% of the nominal value. Sorry, 0.006. This is 3 sigma, right? I'm talking about 99%. So you can see, I mean, this is called yield. How many of the devices that you fabricate will be within specifications? There are yields at different levels. There, when you fabricate chips, there are chips that simply won't work because of some defect or the other. That is there. And after that, you have things like this. Even among the chips that are functional, they may be off the specification, okay, by some amount. So then you can estimate how many chips will be within the specs that you want using this, right? So as far as designer is concerned, you have to be able to estimate the error variance of any quantity. Okay. Any questions about this? Now, how do you go about calculating the effect of this error, component error in any circuit? I'll come to errors in other components, but let's say I have some circuit, it may have an input somewhere and the output somewhere, and there is some resistor which I show outside. Inside it can have bazillion components. Okay. So this is nominally R naught, but can have an error delta R, and you know the variance of delta R by R naught and so on. Okay. So now how will you find out? Basically, the output you are interested in is here. So how will you find out the effect of this delta R in any circuit? I mean, I gave you 4 resistors and a lot of you are struggling with it. So now if I give you an arbitrary circuit, what will you do? How do you do this? Do you recall anything from some basic circuits course that will help you? Yeah, what small signal analysis? Okay. Delta R is a component change, it's not a signal. So, but the direction is correct. We have to go towards small signal analysis of. Now, why do you need a Taylor series? You have only one term, right? 1 plus delta R by R. No, we'll do only the first order, but how will we do that? Of what? That's what. Is that what you want to do? That's what I'm saying. I gave 4 resistors and then it took a long time, and I think most of you didn't do that. So, if you now have a complicated, basically you're saying V naught will be some function of Vi, some 100 other variables, and also R, and you will differentiate this and do this. Sorry, that's what. V naught is a function of R. I mean, R is this value is R, okay, and then no, it's a function of R. I'm not sure what you mean by function of R plus delta R. R takes the value of R naught plus delta R. Yeah. No, this general idea of Taylor expansion is well known, but what will you do in a circuit? Huh? Sorry, ground Vi. But what sort of small signal analysis is this? I've never heard of this. Small signal analysis, you change the value of signals. You don't go and change the circuit, right? Which signal? What is the signal? Where is the signal here? Which voltage? By how much? But yeah, how much will it change? So, you may have heard of this. Have you heard of this substitution theorem? What is it? So, if you have, so first of all, in any circuit, let's say this is the nominal case, right? And the current flowing here is some IR naught. Okay. Now, this changes. This becomes R naught plus delta R, and this current changes to IR naught plus delta I. And I can also write the same thing for the voltage. Let's say the voltage across this was VR naught, and the voltage across this would be VR naught plus delta V. Okay. Or let me keep. I'll do the voltage thing separately. So let me stick with the resistance. Okay. And now I will separate out this one as R naught and delta R series components, right? This is IR naught plus delta I. We don't know what delta I is. By the way, everything else would have changed also. So let me show this in red. Delta I, delta R, and presumably the sorry, not here. This is the nominal case. The output also would have changed, right? Okay. So I'll separate the perturbation from the nominal value. What is the next step here? So you know that the substitution theorem says that in any circuit, any lossy component, you can replace that by or any component you can at that value of, this is not a general replacement, at that particular value of input, right? You can replace any component by a voltage source which has the exact same value as what the component had in the circuit, or a current source. Either one is fine, right? So now I will do it for this particular one. What is the voltage across this? IR naught plus delta I times delta R. Okay. Now this, let me do that first. Okay. Sorry, here what I wanted was a voltage source. I have R naught and I have this voltage will be IR naught plus delta I times delta R. Okay. So now this delta I times delta R product, these are the things that you neglect in first order analysis, right? Both are small changes, product of small changes. So this is approximately IR naught times delta R. Okay. And which can be further written as IR naught times R times delta R by R, because you want to write everything as some function of the relative error, because it's a relative error sigma that is given to you. Okay. Is this fine? So now you can do a small signal analysis of the circuit with this as the source. The source value is, what is it? The voltage across the resistor in the nominal state times the relative error. Okay. So with that small signal analysis, you will be able to find the effect. Yes. Delta I times. Yeah, that's what will come out of this analysis, right? See, if you do the analysis with this voltage source, okay, the branch current will come out as IR naught plus delta I. Okay, so that's what you are trying to find out. Okay, so with this you can find the change in every branch voltage and every branch current, and you don't need to keep VI. This is a small signal incremental analysis. You do now a small signal incremental analysis with this source alone, and you will find the effect of this resistor's error. Okay, so in general, this is how you will have to do that. So all the basic theorems that you learned in electrical circuits and networks are useful or equivalent wherever you learned it. So substitution theorem allows you to replace the change in component with a small signal source. And then the small signal approximation allows you to ignore this, because delta I you don't know. That's what you're trying to find in the first place. But assuming the changes are small, you can neglect that. Okay. After that, you can do small signal analysis. Okay. Then finally, if you have 100 resistors, what is the way to do this? You're not likely to do this by hand. Let's say I have 100 different resistors. You will do this 100 times, or what is it that you will do? Huh? Simulation, but what does the simulator do? How does it calculate? Does it repeat this 100 times? I have 100 different sources. Let's say I want to calculate the effect on this output. Okay, this is off scope for this course, but I want to calculate the effect on the output, but not of one resistor, but of 100 resistors. What should I do? Should I do the calculation I outlined 100 times, or is there some simpler way of doing it? Huh? Oh, what is there to average? We are not now talking about any random thing here, right? We just want to calculate the small signal gain from this source to that output. That's all. That's all we are calculating. See, the randomness comes in the resistor value. Okay, when you are basically when you do it for 100 different resistors, you will multiply by the appropriate delta R by R and add up the variances and so on. So right now this one has, this is just circuit analysis, that's all. All I'm asking is if you have 100 different sources in a circuit and you have one output, okay, should I calculate 100 different transfer functions or is there a way of calculating? I mean, is there a way, easier way of calculating? So again, you can go back to, yeah, what? Reciprocity, right? So what you do is, this is how the simulator also does it. What is reciprocity? There are different details, but in circuits with have only resistive elements or elements of the type V equals IR, you will have this reciprocity. For others, there is some special cases that you can find out. That's probably not treated in electrical circuits and networks. But if you consider Y parameters, for instance, reciprocity says Y12 equals Y21. Okay. So now, how does this help here? Because we have many different inputs and one output. So instead of calculating with so many different inputs, probably separately, okay, you can just put the input here on the other side, wherever you want to calculate the output, and calculate all these in one shot. You do one circuit analysis. That's how reciprocity helps. Okay. Anyway, by hand calculation, you do it whichever way you want, but this is something to know. Again, just to emphasize that all the basic theorems you learn are actually very useful. And in fact, even the simulator does the same thing. It calculates it using reciprocity. Okay. Error due to? Yeah. No, no. You find it with any signal. This is what it is going to be, right? Basically, this part that you multiply with, this is like finding the sensitivity. Some of you were saying, maybe you're also saying, I'll write this F and differentiate and neglect all the higher order terms, right? So if I do that, right, let's say I have this. Now, I can change everything in the circuit, right? V naught plus delta V naught is F of, I could have changed the input, okay, and I could have changed that and so on. So what this does is, it's like taking the Taylor expansion of this and retaining the first order terms of all the variations. Okay. So now, yeah, what I think what you're asking is, let's say you're evaluating, you want to evaluate the effect of R on the small signal gain. So then this I, first of all, you should do small signal analysis with VI, and this nominal current should be the small signal current because of that input. And if you take that I times delta R as the additional source, you will find the effect on that. Okay. You can try it with that inverting amplifier, you can try that one. No, no, I mean, don't think of it as Taylor series. It's just like first order in the quantity that you want to calculate. No, no, no. You always take only one variable. That nominal value of the current is whatever it is. It could be the operating point, it could be the signal current. Okay. So that's all. So then you will find. So for instance, if you did it for this, okay, you can try it and you can just try this on your own. You just try to, anyway, this circuit is so simple that you can write down the expression and find the error, but you can also try putting sources and then finding the transfer function from the sources. And quickly, there is always the alternative representation. So nominally, let's say this conductance is G naught, and you have some voltage VR naught across it. And if this changes by some delta G, this will also change by some delta VR. Okay. So now I will split this into parallel conductances. of G naught and delta G. Okay. And this delta G again, I can represent it as what? Current source. Okay. So I'll have G naught and I'll have this additional current source, which is VR naught plus delta VR times delta G, which is approximately VR naught times delta G, which again can be written as VR naught times delta G by G naught, VR naught times G naught times delta G by G naught. Okay. So this is the nominal current. Okay. So you can do it with either a current source or a voltage source. And in any case, I mean, delta G by G naught and delta R naught by R naught are the same thing, right? If this is the relative error in the resistance, the relative error in the conductance would be so relative error in the conductance is the same as the relative error in the resistance, but with a negative sign. But that negative sign doesn't matter here because you are calculating the effect of different resistors, right? And they'll be uncorrelated. So regardless of which sign you take, finally you will add up the variances. Okay, so it doesn't matter, but just keep that in mind. That's all. So you can either, I mean, this happens with every case, just like this with this Thevenin and Norton equivalents. You can have either an equivalent voltage source to represent the error or equivalent current source, and use whichever is convenient for the context. Okay. Any questions? So this is how you will have to do it for every component. I'll come to others, but basically this is the general idea. Okay. Now what all do we have mismatch in? Mainly we have the resistor. There will be different types of resistors. For each resistor, there will be a different mismatch coefficient. Okay. So the standard deviation of resistor error will be AR square by WL, and this AR will be different for different types of resistor. It could be different for metal resistor, polysilicon resistor, and so on and so forth. And then a capacitor, again, this capacitance error will be inversely proportional to the area. The point is this W and L are what you draw. Okay, this much control you have over the random error. Okay, and in a MOS transistor, we'll take, there are 3 parameters, but we'll just consider 2. So in the saturation region, the current is mu C ox by 2 W by L VGS minus VT square, which can be written as basically this whole thing is called the current factor. Mu C ox W by L is the current factor, and you write it as beta by 2 times VGS minus VT square. So there are 2 parameters, beta and the threshold voltage VT, the current factor and the threshold voltage. The third parameter is actually that gamma, which appears in the expression for VT with body effect. That also varies in the same way, but we won't use it for hand calculation, so let's not worry about it. Now, in case of current factor, what is given is, this is basically the variance of delta beta over beta, and this will be A beta square by WL. A beta will be given to you, and it will be different for different transistors. It will be different for NMOS and PMOS, and you may have a variety of transistors for them which they'll be somewhat different. Okay. Now for VT, it doesn't make sense to specify the relative error, because the absolute value of VT is, it can be anything. It can even be 0, right? I mean, in most CMOS processes, the standard transistors will not have it as 0. But for VT, what makes sense is to have the absolute value that is specified. Okay, I'll again, when I come to the error model of the MOS transistor, it will become clearer. But you can at least see that if VT itself is 0, then there, you can't really specify the relative error. So in case of VT, this will just be variance of delta VT. Okay, not delta VT by VT. It's the variance of the threshold voltage itself, and that will be AVT square by WL. Okay. For any component, the variance will be inversely proportional to the area of the component. Okay. This is because these random errors average out from different parts of the larger area. Okay. This is fine. So we'll see how to, we already saw how to, when you have these random mismatches, how to calculate the effect on the output. We have done it for resistors, capacitors, it's the same thing. For MOS, there'll be a little more detail that we'll look at. Okay. Any questions? So in this case, this random mismatch is not something you can eliminate, right? Only thing is, you can try to reduce it. One is, of course, simply by making the area larger. That sometimes you do. It becomes unwieldy because you may be able to change it by, like, let's say, factor of 2 or 4. But if you have to reduce the error by factor of 1000, then you have to go to circuit techniques. Okay, you can't increase the area by a factor of 1,000,000 just to reduce the standard deviation by factor of 1000, right? But in some cases, there are applicable circuit techniques that can be used. Okay. Any questions on random mismatch? Okay, then. See you all.